and we clearly have lots of these observations, but the problem is that we still aren't sure how these mergers are actually forming, since it's actually quite difficult for two stars to become a compact binary that merges within the age of the universe without them destroying each other or becoming unbound during the course of their evolution. So where do all of these binaries come from? Well, there are two main channels that binary merger formation scenarios fall into, and these are isolated evolution and dynamical evolution. So isolated evolution occurs in the field. So this is kind of isolated stars which aren't evolving in an environment where they would interact with anything else. So this involves two stars, they're born together in a binary and they evolve together, undergoing some mechanism, for example, common envelope evolution or chemically homogeneous evolution, which basically allow them to become close without merging before they become compact objects. In the dynamical case, the two components don't actually encounter each other until they've already evolved into compact objects. And this occurs in denser regions of space, like globular clusters, which have typical densities 500 times that of our local region of the universe, and they're even more dense at their cores. So it's thought that in this kind of very dense environment, compact objects can form multi-object bound systems. And if a binary in such a crowded environment interacts with a third component, the system can lose orbital energy to kinetic energy. And this leaves the binary with a smaller separation than it had before the interaction. So repeated interactions of this kind can lead to a very rapid tightening of the binary and can cause a merger within 1,000 years to a few days of the last interaction. So this can cause a very, very rapid merger. So on this slide, you can see a cartoon of an ellipse getting increasingly eccentric, both in its shape and in its hairstyle and accessories. So for field binaries evolving in isolation, the shape of the orbit actually becomes decreasingly eccentric. So that looks like this. And I've taken the liberty of flipping the cartoon around as well, so it's going in the right direction from left to right. So gravitational radiation rapidly circularizes a binary faster than it tightens, and that's according to Peter's equation, which shows that dE over dt is large and negative when E is close to 1. So the larger the eccentricity, the more rapidly it is lost. And as a binary tightens, its gravitational wave frequency increases. So by the time the gravitational radiation from an isolated binary reaches the minimum detectable frequency of LIGO and Virgo, which is about 10 Hertz, it actually has negligible eccentricity. So it just looks like it's a circular binary. Oh, sorry. When a binary is in a crowded environment, though, the situation can be quite different. So what you can see here is a simulation showing how 3 equal mass black holes might interact inside a globular cluster. So the binary starts in quite a stable circular orbit, but as the third object comes in and disrupts things, the orbital radius shrinks and the eccentricity of the binary goes up, so that this binary would merge with non-negligible eccentricity once its gravitational wave frequency was at the detector. And according to simulations by people like Johan Samsing, who created this simulation, and also Carl Rodriguez and Carl Kramer and others, we expect about 5% of globular cluster mergers to be like this one, and to have an eccentricity greater than 0.1 when the signal reaches the detector. Also, this merger remnant could actually go on to merge again, giving us a hierarchical merger in which you can get multiple generations of merger remnants merging repeatedly. And in this way, we can end up with black holes that are more massive than we might get with isolated evolution. So this is kind of an illustration of what an eccentric gravitational wave signal actually looks like in comparison to a circular gravitational wave signal. So on the left, you can see a sketch of a circular signal with frequency and amplitude that increase monotonically until the binary merges. While on the right, you can see a moderately eccentric waveform with an eccentricity of 0.2 at 10 Hertz, so that's at the detector. And because it's moderately eccentric, I've given it this moderately eccentric hat. So you can see that there's a stronger burst of gravitational waves emitted when the binary is at periapsis. So this is when it's closer together, but this decreases when the binary becomes further apart again and the amplitude of the gravitational wave decreases. So in the analyses that I do, which I'll tell you a bit more about later, my analyses are actually limited to an eccentricity that's as high as this. So this is 0.2 at 10 hertz. And that's because of just limitations with the waveform model that I'm using. So for illustrative purposes, although I can't actually probe eccentricities this high, I have included a sketch of an even more eccentric system. So this has an eccentricity of about 0.9 at 10 hertz. And because this binary is highly eccentric, I've given it this very eccentric hat. So as you can see here, the binary emits a really strong burst of gravitational radiation at periapsis, but this decreases to basically nothing when it's at apoapsis. This just looks like a series of bursts. So now we come to the part where I'm going to talk a little bit about how we actually measure eccentricity in these signals, but I'm not going to talk about it in too much detail because it can get quite dry and technical. I'm just going to briefly outline the procedure because I do want to give a shout out to the Bayesian inference software library Bilby, which was primarily developed at Monash in its early days, but is now used worldwide for gravitational wave problems as well as other problems. So usually we do parameter estimation on gravitational wave signals using Bayesian inference. But we can't currently measure eccentricity in this way because eccentric waveform models are really, really slow to generate. And the waveform has to be evaluated within Bayes' theorem, which is shown on this slide, hundreds of thousands of times to fully explore the parameter space. So instead, what we do is we importance sample our parameter space with a quick circular waveform, which shows us roughly where our preferred parameters lie. And then we reweight those posterior probability distributions by the likelihood that we get when analyzing with an eccentric waveform. So this is according to a likelihood reweighting method that was first proposed in Payne et al. 2019. And then my supervisors and I adapted this to the eccentricity case. Okay, so let's look at some measurements that we've actually made using this method. We can look at our first gravitational wave transient catalog, so that's GWTC1. And for this catalog, we found that none of the 10 binary black hole mergers had any support for significant eccentricity at 10 hertz. So in this plot, I'm showing the 90% confidence upper limits on eccentricity plotted against the chirp mass of the binary. And this result is actually consistent with both isolated and dynamical formation, since, as I mentioned previously, we expect only 5% of globular cluster mergers to have eccentricities greater than 0.1 at 10 hertz. So that's 1 in 20, and we only have 10 events here. But in GWTC2, the second gravitational wave transient catalog, we have a lot more. So can we now solve the formation channel mystery? Well, our analysis is still ongoing. However, we do have some analysis for 2 events in GWTC2, and these are these 2 exceptional events. So the first exceptional event is a massive binary neutron star, which is 1904-25. This was more massive than any of the 17 galactic binary neutron stars we've observed with radio observations. So for this event, I'm showing the 90% upper confidence limit on eccentricity, and this is at about 0.07. So this event is not eccentric, not detectably eccentric anyway. However, the story may be different for this other event, which is the very massive binary black hole 1905-21, which merged to give us the first ever direct observation of an intermediate mass black hole. And again, 90% limits are shown, but for 1905-21, it's a 90% lower limit. So this event seems to have an eccentricity greater than 0.1 at the detector. But there are some important caveats to that statement, which I will get into in just a moment. But first, let's look at 1904-25 in a bit more detail. So this was our first exceptional event. This is the very heavy neutron star binary with a binary mass that doesn't have any parallels with galactic double neutron stars that are observed in radio. So we needed an explanation as to why this event was so massive and why we didn't see anything like it with radio observations of the 17 galactic neutron stars, double neutron stars. And why is eccentricity interesting for this event? Well, dynamical formation is not actually thought to be an efficient channel for producing binary neutron stars that merge within the age of the universe. So we were actually not looking for evidence of dynamical formation in this case. What we were looking for here is evidence of something called unstable case BB mass transfer, which is a very long name, but it's just a kind of specific formation channel that we thought might explain the unusually high mass of 1904-25, as well as the radio invisibility of similar systems. So I'm not going to go through what this specifically means for the formation channel right now, but I do have an extra slide with a nice diagram, which I can go through at the end if you like. But essentially, this process can lead to a massive binary neutron star with a characteristic eccentricity, which also merges rapidly enough after forming that it is very unlikely to be picked up by radio surveys. So this is a plot of the characteristic eccentricities from this unstable case BB mass transfer process under different assumptions about supernova kick velocities. So it's plotted over the posterior that we obtained for 1904-25, which unfortunately is quite uninformative, being consistent with our prior below our small upper limit on eccentricity at 0.007. So while this event is actually consistent with having come from unstable case BB mass transfer, we can't actually infer enough about the eccentricity of this event to make any confident statements about its formation channel, which is a shame. However, things do get a bit more exciting for our next event, which is 1905-21, the most massive event ever detected with gravitational waves, with components of about 85 and 66 solar masses. So when they merged, they left behind a remnant that's about 142 solar masses. And this new black hole is also very exciting because it's the first ever directly detected intermediate mass black hole. So when 1905-21 space-time ripples passed through the detector, we saw this very tiny oscillation called the strain, which is pictured in the top right. And this is a very short signal, especially compared to the classic chirp signal that we saw and heard in one of our first slides. So because the objects are so massive, the gravitational waves don't actually reach the minimum frequency that's needed for them to be picked up by the detectors until right before they merge. So we don't really get to see that in spiral at all. And if we play this signal at the frequency that it was actually detected, it's very low pitched and so short that you can barely hear it. So listen very carefully because you may not be able to hear this. It's just kind of a thud. But we can actually frequency shift the signal to make it more audible. And then it sounds like this. And you may notice that in that signal, compared with the chirp that we heard earlier, there was kind of a sense of this pulsation going on. There were these kind of wobbles you could hear. And you'll also notice that the signal that's drawn here has these weird wobbles in it, which do look a bit like the eccentric waveforms that I was showing you previously. But don't draw your conclusions just yet, because first I need to tell you about something else that can give rise to these wobbles in the signal. So the masses of this event were very exciting, but they did give us this very short signal, which made it problematic from both an analysis and a theoretical perspective. So what we actually detected was something very short and fast, like the first waveform that I played you on the previous slide. And a signal this short is very tricky to gain information from because there's less information in the data for us to analyze. It also means that the system must be really, really massive. And it turns out that this system is in the forbidden range of masses that we call the mass gap. So this is a place in the mass range between about 60 to about 130 solar masses, where we don't actually expect to see stellar black holes. And this is right where the source of 1905-21 lies. So we don't expect to form black holes here from normal stellar evolution due to pair instability and pulsational pair instability supernovae. However, one way that mass gap black holes can form is through the collision of smaller black holes in a dynamical environment. So we were looking for the eccentric signature of dynamical formation in this signal. And it turns out that when we apply our eccentricity analysis to this event, it does have this eccentric signature, but it comes with some caveats. So as we saw, the waveform is thought to contain this wobble. And really this wobble is needed to explain some power suppression in the signal right before the merger, because we can't actually see what the in spiral of the waveform is doing for most of the course of this binaries evolution. And as we saw earlier, we can get wobbles like this if our system is eccentric. So when we analyze the system, we got this eccentricity posterior shown on the left, and the prior is shown in gray, while the posterior probability is shown in black. So for this event, we clearly seem to prefer a higher eccentricity, and it actually looks like the posterior is railing against the upper limit of the prior. So that means that it basically wants to go higher than we can actually see with our method. And just as a reminder, the upper limit of our method is eccentricities of 0.2. So for this event, it looks like we actually want to push to higher than eccentricities of 0.2. So is this our first confidently detected eccentric merger? Well, perhaps, but also perhaps not, because in our analyses, we are restricted to systems with aligned spins. So when systems have spins that are not aligned with the orbital momentum vector of the binary, they can precess, and this precession can cause wobbles in the gravitational wave signals too. And the effective precession parameter chi-p is a measure of just how much the binary is precessing. So precession can also be a signature of dynamical formation because isolated binaries tend to have aligned spin, while dynamical binaries can become bound with any spin direction. So they should have an isotropic spin distribution, making them more likely to be precessing when we detect them. So on the right, I'm showing the posterior probability on the effective precession parameter. So this was from our analysis, which we obtained through normal Bayesian inference. And just above that, I'm showing the LIGO-Virgo collaboration's measurement of the same parameter. So you can see that these are very similar and they deviate from the prior on chi-p in the same way. And this is showing us that we have some information there, which when we restrict our analysis to be non-eccentric, does seem to tell us that we have a chi-p measurement. So in order to probe this kind of confusion between eccentricity and precession, in this paper, we performed a number of injection studies using 1905-21-like systems with various eccentricities and chi-p values. And we showed that these two parameters will often be confused for this kind of very massive binary black hole system. So for this kind of system, they're so massive that they merge at very low frequencies. We don't have enough signal in band, and that means that we can't distinguish the two effects. And actually, Juan did some more work showing similar things for head-on collisions, which is kind of like a system with an eccentricity of 1. So either way, if 1905-21 is eccentric or precessing, then it's kind of a clue that it's been dynamically formed. And if it's dynamically formed, then we might expect to see 2 or 3 eccentric mergers in GWTC2 in our second catalog, if cluster mergers dominate our observations. So we need to hold on until we have all of the results for GWTC2 to make that conclusion. But what can we do further into the future with eccentric observations? So as well as studying GWTC2 and future LIGO and Virgo catalogs, we can also use eccentric mergers as probes of globular clusters. So if we have third generation detectors that can see out to very, very high redshifts like the Einstein telescope or Cosmic Explorer, we'll be able to see out to redshifts of 20 and above. So this is interesting from the globular clusters perspective because we're not really sure how globular clusters formed, whether it be during galaxy collisions or in galaxy disks below redshifts of about 6, or in the earlier universe out to redshifts of 12 or 13. So on the left here is a sketch showing the distribution of mergers from a cluster's formation time, and you can see that the eccentric mergers merge faster than others, and this is because they often occur during these dynamical interactions that cause very rapid mergers. And because of this faster merger rate, these eccentric dynamical mergers could be a good tracer of globular cluster formation. And if we have a model for the merger time distribution, like the one on the left, then we'll be able to map our observed eccentric binaries, which are sketched in white on the right plot, back to the underlying cluster birth rate, which is in blue on the right. And we actually had a recent paper demonstrating this idea. So we found that if we assumed 0 error on the distance measurements, our cluster birth time constraints were comparable to or better than the forecasted accuracy of the James Webb Space Telescope after a year of 3rd generation observations. But we are actually in the process of adding in more realistic uncertainties in our revisions, which we should hopefully have finished and resubmitted within the month. Okay, so just to summarize my talk, eccentricity is important for telling us about binary compact object formation and merger environments. It can be useful to tell us about individual events as well as about populations of events. We may well have detected one eccentric event already, but we hope that our O3A analysis will bring us even more. And in the more distant future, 3rd generation detectors may allow us to use eccentric binaries to map the formation and evolution of globular clusters in the universe. So thank you very much for listening, and I would be very happy to have any questions if you have any.
Thank you very much, Isobel. Maybe let's all unmute and give a round of applause. Are there any questions?
So I can start if I may. A first question is, when you analyze this 190521, the massive event under your eccentric model, did you find a huge difference in the rest of the parameters, like the mass, the spins, and all of that of the actual black holes that are colliding? Or it's only a trade-off between precession and eccentricity?
That's a good question. So we actually found similar parameters. They weren't exactly the same because we do have waveform systematics between the different waveform models. For example, the LIGO collaboration used different waveform models to the waveform model that we use for our initial circular search before we do the eccentric reweighting. So they use these kind of waveform models that include NR effects like higher order modes and things like that. Whereas we used a different waveform model, which was IMR phenom D, which is a phenomenological model, which meant that our results were slightly different, but they were consistent. So they looked like they were getting the same regions of the parameter space.
So regarding this reweighting method in which you first explore, so first estimate parameters without precession and then try to add precession, do you expect it will fail for cases in which eccentricity is really, really strong? So your initial model would completely fail to find the right parameter?
Yes, so this is a concern, I think. Possibly not for, or maybe for very high mass events. I'm not sure, but we do need to be certain that we are that we have similar enough waveforms that our circular search does recover the signal power. So in terms of, actually, I think this would be better. So for high mass systems, all of the power that we're seeing really comes from the merger. So we would be able to pick that up with the circular search before we do the reweighting with the eccentric template. But if we had a lower mass system where we could see more of the in-spiral, we might not pick up the power in the in-spiral from a very, very eccentric signal. That might be picked up instead by something like a burst search. If we had a very eccentric signal that had a lot of, of these short bursts and not much in between, the circular search might maybe pick up one of those bursts as a merger or just not pick up the signal at all. So that would be an issue, yes, for the lower mass systems. But for this system, because we only really see the merger, it's less of an issue.
Oh, okay. Yeah, that makes sense. So I only have a last question. So I always struggle to understand if we see that this system shows either precession or eccentricity, which are signatures for dynamical formation, and on top of that shows a black hole that should not be formed from stellar evolution. So yeah, from stellar collapse. But on the other hand, we have this paper from LIGO that actually tried to determine whether this is a first or second generation black hole. and the first generation scenario is slightly favored. So that's something I struggle to understand. I don't know if you realize this and have some ideas on it.
Yeah, I also read that bit of that paper and was slightly confused by it. But I think the formation channel that they propose is that you have a bunch of stellar collisions in kind of a dense environment. So you'd have to be in an environment already where you are able to have stellar collisions. So presumably a dense environment like a globular cluster or something. And then after you have a lot of stellar collisions, you end up with something very, very massive that then collapses directly to a black hole that could be in the mass gap. And I think that's their preferred scenario. I thought that sounded like a fairly unlikely scenario, but looking at some of these simulations from globular clusters, for example, Kyle Kramer has this CMC cluster catalog. You actually see this kind of stellar merger and direct collapse happen surprisingly often. It's like the rates are comparable with hierarchical mergers, that surprised me, but it's something that happens apparently.
Oh, wow. Okay, thank you.
Any other questions? Well, if not, then let's thank Isobel again. Thanks very much.
Thank you for having me.
Okay.